I am Dr. Stefan Franzen, Professor of Physical and Biophysical Chemistry at North Carolina State University. In this episode of PChem Tips, I would like to explore the meaning of the term blackbody radiation. I recall when I first learned about this topic, after reading the book and attending lecture, I understood that quantization of radiation was needed to explain the phenomenon known as blackbody radiation. Without any historical background, I understood only vaguely what physical problem blackbody radiation was supposed to solve. Moreover, I had a nagging question. What is black about a black body? The sun is a black body, so are the stars and planets, every object in the universe, and even the universe itself. Why are these celestial objects called black bodies, when some of them are very bright? By the mid-1860s, scientists saw the universe in terms of Newton's laws, Maxwell's equations, and thermodynamics. Thermodynamics was still under development. Gibbs formalized the subject that we know today in the 1880s. What is the connection between thermodynamics and radiation? That is to say, thermal radiation. Scientists knew that if they wanted a unified picture of the solar system, and by extension the cosmos, it was necessary to understand the relationship between light and heat. We all know that we can feel the sun's radiation as it continually impinges on the Earth. If there were no loss mechanism, the energy of the Earth would increase as radiant flux from the sun was absorbed. Ultimately, the surface of the Earth would reach the temperature of the sun. Since we are not living on a fireball, the Earth must emit or reflect the same radiant power that it absorbs. As a perfect blackbody absorber, according to Kirchhoff's ideal picture, the Earth would absorb all the incident radiation from the sun. There are two loss mechanisms. The atmosphere reflects 30% of the incident light, known as albedo. But what happens to the other 70%? Kirchhoff also hypothesized that the emissivity of an object must equal its absorptivity. This is intuitively understood. For example, we know that good reflectors are poor absorbers. So, the Earth emits radiation at a rate that compensates for the incoming solar radiation. The Earth's emission is much weaker than the sun's radiation, since only a tiny fraction of the sun's radiant power strikes Earth. Even if we had no way to measure the Earth's emission spectrum, we can recognize that the emission wavelength must be much longer than the wavelength of visible light. In fact, the sun's emission spectrum is peaked near the visible region, around 500 nanometers, or half a micron of wavelength. And the Earth's emission spectrum is peaked around 11 microns. It was known empirically since 1864, when Tyndall invented the platinum filament, that there was a relationship between temperature and emission wavelength. In 1896, that relationship became known as Wien's displacement law, when it was derived in a formula that's close to the Planck equation we'll consider later. Another observation from that time that required explanation was the unusual dependence of radiative power on temperature. The flux, measured as power per square meter, increases as the fourth power of temperature. This stunning deduction, published by Joseph Stefan in 1877, became known as the Stefan-Boltzmann law. Why was Boltzmann's name associated with that? Ludwig Boltzmann's theory of thermally populated energy levels as a microscopic explanation for thermodynamics affected science deeply, although his work was not accepted during his lifetime. Sadly, Boltzmann committed suicide in 1902, which was just the time when many scientists were starting to realize the validity of his theory. As we shall see, the idea of treating radiation as a harmonic oscillator with discrete energy levels was necessary for Planck's theory that explained thermal radiation observations quantitatively. Although the topic we are considering is most accurately called the effect of thermal radiation, for historic reasons it has become known as blackbody radiation. There is no way to change the nomenclature, but we can point out the equivalent name that perhaps gives different insight into the intersection of thermodynamics and radiation physics. For example, the emission spectra of stars show the dependence of Wien's displacement law. This figure shows the normalized spectra of 3 stars, which have temperatures of 20,500 Kelvin, 5,800 Kelvin, and 3,400 Kelvin, and wavelength maxima of 140 nanometers, 500 nanometers, and 850 nanometers, respectively. The intensity of spica would be approximately 60 times greater than the Sun if the spectra were compared on the same scale. Finally, I should observe that these are drawings, and the measured spectra of stars show significant sharp dips. These are best known for the solar spectrum, of course. They are called Fraunhofer lines. Perfect emissivity is an ideal case, but real stars consist of elements that can absorb radiation at particular defined wavelengths. But let's not get ahead of the topic. Planets emit as well, but because of their significantly lower temperatures, their emission is both much weaker and shifted into the infrared region or even the radio wave region of the electromagnetic spectrum. Planetary emission is so weak that it is extremely difficult to measure, with the exception of emission from Earth. Satellites can measure the emission and also the absorption by gases in the atmosphere. These too cause significant deviations from Kirchhoff's ideal picture. Stars and planets provide some information, but there are no knobs or controls that permit one to systematically change the temperature and observe the changes in intensity or wavelength. In fact, we only know the temperature of Spica from its emission maximum, since Spica is 261 light-years from Earth. There's no other way to know its temperature than from the spectrum. The breakthrough on the experimental side came like a light bulb. I mean to say it came as a light bulb. It is possible the reason that we associate the light bulb with having a new idea. Tyndall's platinum filament gave some insight, but the tungsten filament light bulb was much more robust. The temperature, radiant flux, and emission wavelength could be changed simply by modifying a current flowing through the filament. The tungsten filament light bulb was invented in 1879. The Rayleigh-Jeans law describes the emission from a spherical cavity emitter with a continuous distribution of electromagnetic frequencies. Maxwell's equations give no basis for assuming anything different than a continuous distribution. Classical electromagnetic theory predicts a linear temperature dependence of the energy, very different than the observed fourth power dependence. It clearly does not explain the Stefan-Boltzmann law. The functional form of the Rayleigh-Jeans theory increased without bound as the wavelength approached zero. There was no maximum, so this theory was inconsistent with the Wien displacement law. The solution came in 1900 with a theory advanced by Max Planck. After many attempts, Planck applied Boltzmann's statistical mechanical theory. However, Boltzmann's theory had been ridiculed, so it really was Planck's theory of last resort. Once Planck applied the thermal average of an energy ladder, which was equivalent to Boltzmann's treatment of the harmonic oscillator, he realized there was no reason that the frequencies in the spherical cavity emitter needed to be continuous. Planck assumed that the radiation cavity modes were evenly spaced by an energy h nu. That implied that the levels were quantized, that is to say numbered, 0, 1, 2, 3, etc. In the beginning, Planck had no idea what the constant h was, but by the time the theory had been developed and used to explain thermal radiation and the effects of the Stefan-Boltzmann and Wien displacement laws, the value of h was constrained and known with reasonable accuracy. In addition to energy levels, Boltzmann's statistical mechanical model assumed an exponential energy proportionality between the population of any two microscopic states. Small p sub I or j represents a population. The probability, designated by capital P sub I or j, is the population of a given state divided by the sum of the populations of all states. The sum of the populations of all states is known as the partition function. That is, the ratio of the population in a single state to the total population gives the fraction in that state. You could think of that as partitioning the states by their probabilities. the relative probabilities are equal to the relative populations. I do not mean to disparage Max Planck by pointing out the reliance on Boltzmann's theory. It is a shame that the scientific community was not more open to new ideas, but experiments forced the issue. Planck's contribution can be seen as very simple. He set the harmonic oscillator energy level equal to the energy of an electromagnetic wave and defined that energy as h nu. Yet the significance of saying that the electromagnetic cavity modes are quantized is enormous. Planck's theory implies, for the first time, that light can be viewed as a particle, a photon. Once the system was defined as a ladder of equally spaced energy states, Planck could use Boltzmann's solution for the average energy of the harmonic oscillator. In the high temperature limit, which is also the classical limit, the average energy is known to be Kb, Boltzmann's constant, times temperature. At lower temperatures, the average energy of such an energy ladder is equal to the spacing h nu divided by the sum of the populations of all the states. The form you see here is justified in Derivation 1, which is accessible as a video associated with this episode. The Planck distribution is obtained by substituting the classical average energy, kBt, with the average energy of the harmonic oscillator, shown in the red box. One of the tenets of quantum mechanics is that the energies and behavior of states should approach classical behavior in the limit of high temperature and high quantum numbers. The high temperature limit means that h nu is much smaller than kBt. The same is true of hc over lambda. This means that the exponential term in the denominator can be expanded using a Taylor series because the exponent is very small. It is also a good approximation to take the series only as far as the first term. As shown here, this leads us back to kBt as the classical average energy, as required. The spectral energy density given by the Planck distribution is compared to the Rayleigh-Jeans law on this slide. One can see that the line shape of the Planck theory is reasonable. There is no ultraviolet catastrophe, since the Planck distribution is a peaked function. The proof that this model is appropriate can be obtained by showing that it explains both the Wien displacement law and the Stefan-Boltzmann law quantitatively. The Planck distribution function has the correct form to explain thermal emission spectra of stars or light bulbs or any radiant objects. It is a peaked function with a peak that is inversely proportional to temperature, and its integrated area increases as the fourth power, consistent with the Stefan-Boltzmann law. The Wien displacement law should logically be found by calculating the maximum wavelength of the Planck distribution. This figure shows the derivative with respect to wavelength and an equation where it is set equal to 0, the prescription for finding a maximum in calculus. Yet when I have tried this method of calculation, I end up with a tautological solution. The derivation published in 1896 by Wien begins with a slight modification of the Planck expression, provided in Derivation 2. The distribution used by Wien is the same as the Planck distribution in the low temperature limit. That is to say, the limit where kBt is much less than h nu. There, Wien's derivation is exact. Unless I'm missing something, the Planck law cannot be rigorously proven to give the Wien displacement law at all temperatures. However, empirically, the peak of the distribution shifts with temperature in the manner predicted by the Wien displacement law. Thus, at a minimum, Planck's result is consistent with the Wien displacement law. The Stefan-Boltzmann law is obtained by integrating the Planck distribution. The solution is analytic and agrees accurately with the observed temperature to the fourth power dependence. This dependence is so unusual that this agreement is strong evidence for the validity of the model. The integration is described in Derivation 3. This figure shows the Planck distribution plotted at 4 temperatures. The distributions have not been normalized, so there's a large change in integrated area that is readily apparent. For example, the plot at 2000 Kelvin is 16 times larger than the plot at 1000 Kelvin. The ratio of the temperatures is 2, and 2 to the 4th power is 16. So this is a manifestation of the Stefan-Boltzmann law. The shift in the maximum position is also evident at the 4 temperatures shown. Classical physics fails to explain the thermal emission spectra of light bulbs, stars, or other bright emitters whose spectra we can easily measure. Planck resolved the dilemma for physics by accepting Boltzmann's model for a system of evenly spaced energy states. That was first used to explain the harmonic oscillator. We will later show that the quantum mechanical harmonic oscillator does indeed give such a solution. In order to be quantitatively consistent with the Wien displacement and Stefan-Boltzmann laws, Planck's constant h must have a value of 6.626 times 10 to the minus 34th joules seconds. Note that the units are units of action. When multiplied by a frequency, the unit of h nu is joules, the appropriate unit of energy. Aside from the predictive power for many radiant objects, Planck's result is useful for explaining the effect of an absorbing atmosphere on the temperature at the surface of a planet. That application is described in episode 2.